Welcome everyone to this presentation. My name is Mackenson and I'm a research fellow at Twitter. This section will focus on how quantum computing can be applied to one of the most challenging global problems, understand and forecasting energy demand. This project was in collaboration between the research team and our partners at E1. Today, I have with me two members of my team, and Baron and Aditi, that will also speak in this presentation. So, if you're interested in collaborating further, or if you have any question after this presentation, feel free to reach out at this email show here. We always open to research, partnership, collaboration, and quantum application in any area, energy, materials, etc. A quantum computing for a smart network. And this section, we focus how quantum technology can enhance the intelligence and efficiency of modern energy network. Today, grids are becoming increasingly smart, integrating renewable energy, electric vehicles, and automatic control system. But this network grow more complex and decentralized. They generate massive amounts of data and require faster and more adaptive optimization method. This is here where quantum computing begin to play a transformative role. Now we have set the context of why quantum technology are important for a smart renewable driven network. Let's dive into the specific challenge the network face and how quantum method can address them. Historically, the power flow was very simple and predictable. Electricity moved in one direction from large power point to the transmission system, download to the distribution network at the end and the user. These diagrams show this traditional and linear method. So one of the biggest structural challenge happening in energy system today is shift from centralized generation to highly decentralized generation. And the traditional grid energy flow in one direction from large centralized power point to transmission line, then distribution network, and finally to the consumer. This structure made planning and forecasting relatively simple and controlled with low variability. But the smart grid looks completely different where the energy flow in multiple direction because generation now happens in multi-point, for example, and rooftop, solar, white farm, community storage, and industrial seat, and more. Consumer are also become prosumer, sometimes consuming energy and sometimes producing it. This shift to decentralized energy create enormous benefits. For example, regeneration, resilience, and flexibility, but also major challenge. This variability and uncertainty introduced by renewable require more sophisticated forecasting, optimization, and real-time decision making. This is precisely where advanced technology like quantum machine learning can begin to offer a significant values. Now we have shown how the structure of energy network is transforming. Let's explore the new kind of forecasting and optimization challenge this transition introduces and why quantum approach are particularly suitable to address these problems. Now let's take a closer look at what define a smart grid. As we shift away from a centralized energy model, the grid evolved into much more dynamic and complex system. This slide have three of the most property that characterize in a smart grid. One, the more diverse portfolio of energy source. First is a smart grid integrate a far more diverse mix of technology generation. Until focus only in thermal plant, today grid incorporate solar, wind, storage system. This diversity increase resilience and sustainability, but also increase variability, which put pressure and forecasting on grid management team. The second characteristic is more point energy of energy consumption from electrification. This point is the electrification is expanding from home to transportation, industry, and data center are all major new loads that not exist before this energy transformation. Each of these consumption points behave differently. The smart grid must be able to monitoring, predicting, optimizing these high distributed dynamic loads. The, the third property is decentralized energy generation and resource allocation. This third, perhaps the most important, the smart grid is fundamentally decentralized. Energy can be now produced and at home business, farms, and community installation. This decentralization means that energy and resource flow in many directions, not just one. This requires new form to coordinate, optimize, and allocate energy. So these three properties together create a grid that is cleaner and more flexible, but also more complex. This is where advanced computation method, including quantum machine learning, become extremely valuable. The quantum method can offer the potential to extract pattern and optimize decision, and why that scale more naturally with the complexity of the problem. Now we identify the main key characteristic of the smart grid. We'll see how you can use quantum technology to address these problems. So as decentralized generation become the norm, grid management has to evolve from a simple centralized control structure to a high dynamic distributed system. This slide illustrates two sides of the challenge: real physical neighborhood where many homes have rooftop solars, and the abstract network representation of energy flow between these distributed nodes. We have three, uh, three aspects in this challenge. The first is peer-to-peer trading. With distributed generation, household can trade energy directly with each other. This requires real-time optimization, matching buyers and sellers across the network, often second-by-second resolutions. And also the second is the dynamic pricing. In this case, a price adjusts dynamically as supply and demand shift across this network. And the third is supply and demand prediction. Forecasting become more difficult until of predicting on central generation curve. We must forecast the production and consumption and thousands of millions of micro generators and flexible. This grid need accurate, high-resolution prediction that remain stable and avoids overloads. This is exactly the kind of problems high-dimensional, graph-structured, and rapidly changing where quantum computing can have the potential to outperform the classical tools, and quantum model naturally in the relationship across large network and can optimize complex integration between distributed nodes. So in this slide, you can see how the quantum method can offer meaningful advantage at the scale of the problem grow. And this graph, we have many outs. In this case, we have in certain point, we have some quantum advantage, and the 100 to 800 households, the classical and the quantum model perform has the same performance, but when you increase the scale, we can see we have some quantum utility as this point, where we can use the quantum technology to take these advantage. So we have to the main goal of this project is to develop quantum machine learning method to predict energy demand and decentralized grid model with advantage or possible advantage of a classical method. In this case, you use we met quantum algorithm, quantum Gaussian process, and quantum reservoir computing. And also we use the classical match, the classical Gaussian process and echo estate network. So for example, the Gaussian process is a powerful probabilistic method that go beyond simple predictions. Unlike model that provide a simple best guess, this model a this model a distribution of a possible function that fits and the data that not only provide a prediction, but also deliver a full uncertainty qualification. That is very important to make informed decision and energy demand. And the other quantum method is quantum reservoir computing, use the natural dynamic of quantum system as a computational resource. Instead of training a large neural network, you drive a quantum system with put signals, and the quantum evolutions create a rich nonlinear mapping. And then only the output lies training and making this approach fast and scalable. And also to compare these two quantum model, you use classical benchmark. The first is classical Gaussian process. This is the a gold standard for probabilistic time series forecasting, where we compare the quantum Gaussian process against this classical version to test whether quantum kernel is add some values and the prediction problem. And also we have the echo-state network. It is a classical analog of a quantum reservoir computing that this provide a rigorous baseline to evaluate presentation capability for complex demand behavior. And also, in addition, these two specific method, we also investigate other specific method to enhance the quantum algorithms. In this case, we work specifically with associated quantum kernels to reduce overfitting and also to mitigate exponential concentration. Uh, Also, we calculate potential or identify potential advantage, and by use a time series data set that this specific topic will speak later. Uh, Also, the prediction we want to do is between a tolerance error between 15 and 20%. So, and in this case, we have these four specific this graph when you have two quantum model and the classical baseline, and also and the P represent the calculation for a possible quantum advantage and some specific data set. In this case, we calculate the geometric test and complexity calculation to predict some quantum advantage and a specific data set. So specifically in the quantum Gaussian process, we using the projected quantum kernel. We use the projected quantum kernel until using the fidelity kernel, because the projected quantum kernel help to reduce noise. Because in the fidelity kernel, you use we compare the full n qubits, and the projected quantum kernel, you measure a local Pauli basis, and this reduce the the noise that can introduce in the quantum hardware. So this and this is the architecture of the circuit we are using for the positive quantum kernel. At the first layer, we encode the data set of each customer and this rotation gate. And to use the correlation between customer, we introduce entanglements between each customer data set. In order, we can use the entanglement property of quantum computing in order to 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 capture correlation a pattern between customer consumption and the data set.
Okay. Regarding the quantum reservoir computing, actually we'll start with the two lines of classical reservoir. It uses a fixed recurrent network to transform time series inputs to rich temporal features, which is a sim and then which is a simple readout layer which learns from this quantum this reservoir. Now the idea of QRC also follows the same idea, but replaces the classical reservoir with the quantum systems, whose natural dynamics provide far more expressive nonlinear transformations. So here in this model, we take the classical time series value and converted it to into the quantum data, that is using parameterized quantum circuit. So the one input, right, one feature of the quantum value is specific with the one parameterized circuit, which is we can see here u of one, and then u of two, and then u of two, and then in each that block of quantum circuits, it will look like Rx of S of ut. So that it's a specific point. And then along with the system qubits, right, we use two ancillar qubits. They interact with the systems through C naught gates. I mean, like they estimate the data from the system to ancilla, because we cannot disturb the system. It will break the reservoir. We have to estimate with the, I mean, like we have to build one more ancilla system. We have to measure only the ancilla system till the end without disturbing the main system. And after collecting the data, I mean, like after measuring out, we can reset and reuse the ancilla qubits. So this is the simple architecture of the QRC, and at the each step, the reservoir keeps evolving in the main qubits, and the ancillas extract information from the reservoir. And coming to the next slide. Okay, so the parallel quantum reservoir computing extends the basic QRC model. So in this, we can process multiple time series at the same time. Like instead of having the single reservoir for one input stream, we can create multiple quantum resistors, and each one acts as an independent reservoir. So this allows us to handle several input sequences in parallel. Okay, and depending upon the design, we can design the architecture in the so many ways. Depending on the design, we can use separate ancillar qubits for each reservoir, or let them share the information, or we can use half of the ancillar bits. How many qubits we use in the each uh, qubits in the reservoir. But overall, the main idea is we can develop multiple time series in parallel. Okay, so this slides show the full pipeline of the parallel QRC architecture, right? So see, each time series first goes through an encoding step where its value is transformed into a quantum operation inside its corresponding register. As I said, it's a parameterized circuit. You can see here Q1, Q2, QS. These are the independent time series encoding. And after encoding, the reservoir qubits evolve, I mean, like naturally, they generate complex internal dynamics. So at the next step, what we will do means each reservoir has an respective ancillar qubit that interacts with it, and only the ancilla is measured. We can see. So the interaction is nothing but estimation by using C naught gates, right? So these measurements gives us feature values, one from each register. All these feature values are combined to form a single feature vector for the time step. So for one feature, I mean, like for one at one time step, we will have one feature. I mean, like feature vector at the end of the time step by using ancilla measurement. Okay. And then finally, the feature vector goes into a kernelized reroute layer, typically using an RBF kernel. In this research, we use RBF kernel, but we can use many more kernels. So this layer maps the quantum features into a space where regression becomes more effective. The output of the regression model gives us the final forecast. Finally, the architectures let us use the quantum evaluation to the multiple time series data with proper and a clean architecture overall. Thank you. This is all about the quantum QRC. And I think Aditi will continue from this slide. Go on, Aditi.
On this slide, I want to explain why classical machine learning can often match the performance of quantum machine learning. Now, you see the Venn diagram here shows three regions. First, we have BPP, which represents all the problems that classical probabilistic algorithms can solve efficiently. Second, we have BQP, which represents the set of problems quantum computers can solve efficiently, while BPP is fully contained inside BQP, meaning anything classical can do efficiently, quantum can also do, and sometimes more. Now, the interesting part is the large blue region, which talks about classical ML with data. Now, this region overlaps with BPP as well as with BQP. That means classical machine learning models, given enough data, can solve tasks that fall inside the classical domain, but also approximate tasks that theoretically belong to the quantum domain. So, technically, the key takeaway from this slide is even though quantum computing is more powerful in theory, classical machine learning can sometimes reach similar performance simply through data driven approximations without needing quantum hardware. Now that we have seen why quantum advantage depends on the data set, the next question is how do we formally compare classical and quantum machine learning? Now, the work that we have done has been worked upon three tests. But before any of this, we are led to important questions that are shown here. First is, does there exist a data set where quantum machine learning significantly outperforms classical machine learning? Now, this is still an open question, and it's crucial because most reported quantum advantages rely on very specific or synthetic data sets. Second is, can classical machine learning generalize just as well if it's given enough data? Now, in many cases, classical models can catch up simply by learning from larger data sets, which challenges the idea of a guaranteed quantum advantage. In our work, we explore this very issue. We focus on examining quantum advantage on any given data set, and then we test this using kernel based algorithms that my teammates have already discussed to align the evaluation with the structure of the algorithm itself. Now, two key insight that guide our analysis is first one, the effectiveness of quantum kernels depends strongly on the structure of the data sets. It is not universally better. And most importantly, geometric difference. There's something called a geometric difference test, which we'll see later, becomes the core metric for assessing where a quantum model truly has an advantage over classical ones. So, this slide sets the stage for why this approach is needed. The advantage isn't automatic, it must be demonstrated through a geometry and structure of data. Now, how do we formally compare classical and quantum machine learning? Now, In our work, we have technically explored upon three tests, and these tests together tell us whether quantum machine learning actually has an advantage. The first one is the geometry test. Now, this checks how similar classical and quantum kernels are. If the geometry of the classical feature space closely matches the quantum one, then classical machine learning will perform just as well. But if the quantum kernel captures the structure that the classical kernel cannot, the quantum advantage becomes possible. The second is the complexity test. Now, here we compare how well a classical and a quantum models generalize. Even if a quantum model represents data in a richer space, it only matters if we can generalize better than classical machine learning. So this focuses on sample complexity and learnability. Third is the dimension test, which you see in the diagram lies towards the left hand side. This measures the effective dimension of the quantum feature space. Now, if the quantum dimension is too large relative to the dataset size, quantum models may overfit or become hard to train. So the flow chart on the right summarizes how these tests interact. First, the geometry test decides whether the classical model already matches the quantum one. If not, we check dimension to see if classical machine learning can still learn the quantum feature space. And finally, we use the complexity test to decide whether there is a real prediction advantage. So overall, these tests together determine whether quantum machine learning has a true advantage. So technically, the key parameter driving these decisions is the geometric difference between the classical and the quantum kernels. Thank you.
As we sort of the technical portion of this presentation, I want to highlight several key research direction that we will shape the next stage of quantum machine learning for energy application. Each of these direction address a limitation or potential area of improvement that can unlock performance in quantum machine learning. First is advanced error mitigation. Current quantum devices are still noisy, which directly impact the reliability of quantum kernels. To make a quantum model robust, we need to better noise reduction technique that preserve the structure of the quantum feature we extract through noise resistant measurement grouping. And also the second is reduce the kernel complexity. Even though the projected quantum kernels are very powerful, but they can become computationally expensive at the system scales. Future research will focus on scalable approximation for n-body kernels and adaptive projection technique to keep kernel name usable and for large scale energy forecasting. The third point is optimizing NCR qubits and quantum reservoirs. NCR qubits play an important role in enhancing the nonlinear processing power of the quantum reservoir. However, the best way to configure, reset, and entanglement them is still an open problem. Optimizing NCR behavior will unlock significant richer reservoir dynamics. At, at the end is scaling household forecasting. Finally, we want to push quantum forecasting to much larger number of households. Our objective is to build quantum model capable of forecasting entire communities or even city-level energy demand with high accuracy using efficiency qubit encoding by and hybrid quantum classical networks. All these direction, error mitigation, kernel simplification, and LCR optimization and large-scale forecasting form the roadmap for the next generation of quantum energy analytics. As quantum hardware merge, each of these research take become increasingly practical quantum advantage and smart green forecasting. Thank you for your attention and your interest in this specific topic. If any of this research direction resonate with your with your interest and your work. We will be happy to explore our collaboration. Please reach out in this email at any time and we can answer. Thank you very much.